Okay guys, we are going to start our last review other than the final for your last test of the whole year, and that's going to be over stoichiometry. So just remember that stoichiometry is literally just a ratio. You're finding out the relationship of different units according to the ratios of their coefficients. So whether you're given molecules or atoms or formula units, it's all the same thing. Okay? Or you're given a mass, so grams in 10th grade, it's only grams, and you may be given a volume, okay? So this is liters of gas, not liquid. So you may be given one of these units. If you're given one of these units, you must convert to moles, okay? And if you, in the question, if it's not asking for you to answer in moles, then you're going to have to convert back to one of these units, okay? So if you're not asking, if the question isn't asking you to answer in moles, you'll have to convert back to one of those. So that's all we're doing in all of these equations. That's it. So you're either going from one of these to moles back to them. You may be given moles and you have to go back to them. You may be given one of these and you want to stop at moles. It all depends on what the question's asking. So we're going to go ahead and get started on our review, so it's not too long of a video. And hopefully we can do it quickly enough to retain your attention. So the question says, how many moles of calcium nitrate would react with 4.55 moles of chromium 3 sulfate to produce calcium sulfate and chromium 3 nitrate? Okay, so the cool thing is they've already done our equation. We don't have to come up with the equation ourselves. It even balanced it for us. So all we're doing is going, we need to write our known and our unknown, okay? So it only gives us one known, okay? So that means we're only just doing a conversion. So we have a known, so that's 4.55 moles, okay, of chromium 3 sulfate. So that's this thing, okay? So Cr2SO4. 3, okay? The unknown is just what it's asking for. How many moles of calcium nitrate? So it's asking for how many moles of calcium nitrate. So that's this thing, CaNO3, okay? So now we're going moles to moles. So if you'll look at our little flow chart, we go moles to moles. We don't have to do any of these conversions. We don't have to deal with molecules, grams, or liters. It's just moles to moles. So all we have to do is just the mole to mole ratio. So we start out with what we know always. Okay, 4.55 moles of Cr2SO4 3. And then we have to do a mole to mole ratio. If you didn't do a mole to mole ratio in stoichiometry equation, you've probably messed it up. Whatever's up here, whatever unit is up here, must go down here. So this will just be transferred here. Moles of Cr2SO4 3, okay? And then what unit we're trying to get to, okay, here. Moles of CaNO3, okay? So that's that, and we need to put our ratio. So CaNO3, so that number is going to go here. Cr2SO4, that's right here. The coefficient is actually 1, okay? So we're going to put 1 here. So now all I have to do is to get my ghetto calculator that I stole from Mr. Kramer, okay? And I type in I don't know if that was cleared, 4.55, okay, times 3. We can ignore the 1, because 3 over 1 is the same thing as 3. So times 3, and our answer is 13.65. 13.65. The moles of chromium sulfate cancel out, and we're left with moles of calcium nitrate. So the answer is 13.65 moles of calcium nitrate. Is that what the question's asking for? How many moles of calcium nitrate? Done. Okay. Easy. Moving on. Next question says, how many moles of zinc would be produced from the reaction of 13.2 moles of copper with excess zinc acetate? Copper 1 acetate is the other product. Okay, so they did it for us. Again, that was nice, but we have to balance, okay? One key hint that you have to balance is this right here. You have these lines, okay? We didn't have that here. So make sure that if these lines are here, you need to balance it. One copper, one zinc, 2 acetates, only 1. Okay, so we need to write 2 here. So that means we have 2 and 2, that's good. We have 2 coppers, so we need to change that here. So 2 coppers, 1 zinc, 2 acetates, 2 acetates. Is that acetate? Yeah. Okay, you can go ahead and put 1 if you want to, or you can assume the 1, it doesn't matter. So the question, it only has one known, okay? So we're not like comparing and trying to find a limiting reactant. So the one known is 13.2 moles of copper. So we're talking about this thing. So moles of Cu. Unknown is how many moles of zinc? So how many moles of zinc? Easy, okay? So again, we're not trying to find mass, we're not trying to find formula units, we're not trying to find liters, we're just dealing with moles. So it's just that one-step problem and that's it. So you start with your known 13.2 moles of Cu. And then you have whatever's here. Again, we'll go here, okay, moles of Cu. And then up here is our unknown, moles of zinc. Okay, now we find our little ratio. So zinc, it's a 1, copper, 2. Okay, so now we plug it into our calculator. So we clear it, 13.2, and then the 2 is at the bottom. So since it's that, it's 13.2 divided by 2. And that's it, 6.6. So the answer is 6.6. The moles of copper cancel and you're left with moles of zinc. Moles of zinc. Guys, this process like right here, that's called dimensional analysis, okay? Dimensional. If you haven't been exposed to this, it's very important. You're going to see it in math class, you're going to see it in science classes. This is super important as far as converting things, okay? And that's mostly what stoichiometry is converting. All right, moving on. Next question. What mass of gallium chloride would react with excess fluorine, that just means extra fluorine, to produce this much, 78.9 grams of chlorine? Gallium fluoride is the other product, okay? So they wrote our formula for us, they've balanced it for us. If this is difficult for you, go visit Unit 6 and 7, the test review. All right, so our known and unknown. Okay, so the known is this. There's only one, so we know we're only going to do one equation. So 78.9 grams of chlorine. Okay, remember chlorine is a diatomic element. And then our known, our unknown is what mass of gallium chloride. So mass of gallium chloride, okay? So we have our known and our unknown. This is a little different than this problem because we were going from moles to moles. And as you remember, just moles to moles, it's just that one single step issue right there. That was easy. But we're actually given, let me show you. We're actually given grams. We have to go from grams to grams. So in order for us to do that, we have to go from grams, okay? So that means we go from grams to moles, and we have to go from moles to grams, okay? We're actually going to grams again, okay? So make sure you know that. If you're not given moles or asking for moles, you're gonna have to do this conversion, and that's why you know all of those different constants, like liters and grams and moles. Speaking of, I'm going to need a periodic table. Oh, sweet, got one. Okay, so we have that. So we have grams, we need to go to moles, and then grams. So we always start with what we know, 78.9 grams of Cl2, okay? Whatever's here must go here, so grams of Cl2 over 1 mole to convert. We need to do 1 mole of Cl2, okay? So, to find out what grams, what number that goes there, we look at how much chlorine weighs, okay? And if you can see, I don't know if you can see, but it weighs 35.45. I don't know, we can go 35 or 36, I don't care, I'll go 35. 35 grams, okay? But actually, sorry, my bad, that's actually not right because that's 35 grams per 1 chlorine, but since it's diatomic, it's actually 70. Whoops, 70, okay? Now, moving on, we need to do our mole to mole, okay? So again, whatever's up here must go at the bottom of the next section. So moles of chlorine, okay? And then moles, this is our mole to mole ratio. It's always there, okay? You see, this had a mole to mole ratio. This had a mole to mole ratio. Everyone will. All right, so what you aren't dealing with anything else other than what the chlorine right here and gallium chloride. So if it's not one of those, we're not dealing with it. So here, our gallium chloride, Cl3, our unknown goes at the top. So here, we're going to put the number 2, will go here. Moles of chlorine, that'll be 3. We get this number from here, okay? So that'll cancel out our moles of chlorine. Now, with that canceled, this canceled, we are now with moles of gallium chloride. Is the question asking for moles of gallium chloride? No, it's asking for grams of gallium chloride, okay? So now that we've converted to moles so we can do our mole to mole ratio, we need to convert it back to grams just because that's what the question's asking for. So in order to convert from grams, okay, 1 mole always of gallium chloride will weigh a certain amount. So how to find out how much grams of gallium chloride will weigh? That's when you look on the periodic table. This is all stuff from the beginning of the year, actually. So gallium is right. I just saw it on the phone. Okay, gallium is, we'll say 70, okay, grams per mole. But we have 3 chlorines, okay, and chlorine is 35. So there's a 170, like a single 70, and then 335. So we'll go ahead and do this on the calculator because if I can screw it up, I will. 30 times 3. And then we'll add 70, which is just going to be 175, but just because. All right, so 175. So that's where we figured out our mass of gallium chloride, okay? So you want to make sure everything crossed out. Our grams of chlorine crossed, our moles of chloride, moles of gallium chloride, and then we're left with our grams of gallium chloride, which is what we are looking for, okay? So when you type this in your calculator, this is super simple. Don't like overdo it. So we take the 78, if you can see, I'm going to try to do this all in one screen. So we'll take 78.9, okay? Ignore the 1, and you can just literally type in divided by 70, okay? And then there's a 2, so you need to times it by 2, divided by 3, go back up here, times it by 175. So if it's on the top, you multiply it. If it's on the bottom, you divide. It's just that simple. Equals. So if you want to put these in parentheses and put it all in your calculator, that's fine. I just do it the way I just showed you. So the answer is 131.5. So the answer is 131.5, and here's our units, grams of gallium chloride. Okay, there, we're 1/4 done. Moving on, how many grams of ammonium carbonate are needed to decompose in order to produce 6.52 grams of carbon dioxide? Ammonium oxide is the other product. So this looks like they've done it for us. We just need the decomposition. It says decompose, that's how we know. So we just need to balance it and then write our equation. So it only gives us 1 known, okay, so we're not doing this excess reactant thing. So we need to balance it. We have 1 ammonia here, 1 ammonium here, so I'm sorry, 2, and then we have 2. We have 1 carbonate. We have, we're gonna have to split this one up. All right, so we have 1 carbon, 1 carbon, 3 oxygens. Okay, that was really easy. So that's it. It's balanced. Anyways, we'll move on. So now we need to write our knowns and unknowns. Not knowns, just one. And unknown. Okay, so our known is 6.52 grams of carbon dioxide. Our unknown is how many grams of ammonium carbonate. So how many grams of ammonia carbonate? Okay. Now what you need to do is you are going from grams to grams. So it's just like the last one, we had to go from grams to moles back to grams. So we always start with what we know, which is 6.52 grams of carbon dioxide. We need to convert it to moles. So in order to do that, we need to cancel out the grams of carbon dioxide. And then we need to get moles of carbon dioxide. Okay. Then we'll do our mole to mole ratio. Then we need to end up with grams. Okay. So what we're doing is whatever's here is here. We need to find out how much carbon dioxide weighs. So in order to do that, you look at the periodic table. Carbon is here. It weighs about 12. So we'll put 12. Okay, and dioxide would mean it has 2 oxygens, so we have 2 oxygens, and oxygen weighs about 16 grams per mole. So we have 16 and 16, okay? So 12, 14, 3, 4, 4. So carbon dioxide should weigh around 44 grams per mole, if I can calculate right. So we'll go ahead and put 44 and 1. This is like a constant, okay? Everyone, these right here are just conversions to and from moles, okay? That's all that is. This is just a ratio. So whatever's here is here. So moles of CO2, okay? And then up here is our unknown, what we want to find out. So NH4. It's such a long molecule. It's quite annoying. CO3, okay? All right, so we need to find our numbers. So CO2, they're 1-to-1 ratio. So technically it doesn't matter, but yes, you could skip this if you just knew it was coming, but I never skip it. So moles here, moles of NH4, 2, CO3, grams of NH4, 2, CO3, okay? So you have grams of that. Oh, we're going to have to calculate that. Okay, for every 1 mole. So we need to find out how much all of this weighs and type in the number. So we have NH4, but we have it twice, okay? So we actually have 2 nitrogens. So nitrogen weighs 14, okay? So we have 2 nitrogens, and they each weigh 14. Hydrogens, we have 4, okay? Hydrogen, it weighs like 1, so we're just going to put 1, okay? So we have 4 hydrogens, but we have that twice, so we technically have 8 hydrogens, so 8 times 1, okay? Then we have carbon. Carbon, remember, weighs about 12. Then we have oxygen, which weighs about 16. 16 times 3, okay? And then you just add all of that up. So, clear. So we have 2 times 14. Could have done that in my head, I guess. 28 plus 8 plus 12 plus 16 times 3 plus 48. Okay, so that's 10. I'm not doing it. 16. Okay, I'm doing it. 4, 5, 6, 7, 8. 86. Okay, I've got to do it on the calculator because I know myself. Good thing I didn't trust myself. I'm going to do it one more time. 28 plus 8 plus 12 plus 48. 96. So we don't ever trust my brain, ever. Okay. So that 96 goes up here. Okay? So now all we have to do, we've set up our problem. The grams of carbon dioxide cancel, moles of carbon dioxide cancel, moles of ammonium carbonate cancel, and we're left with grams of NH4 to CO3. Okay, that's what we're left with. All we have to do is plug all of this mess into the calculator and we're done. And it's actually quite easy. All you have to do is take 6.52. Since that we ignore the 1, so we just do divided by 44. Ignore that because it's just 1 times 1 or 1 divided by 1. It's fine. Then we need to multiply by 96, and the 1 we don't really need to do anything with. So our answer is 14.23. I'm going to go ahead and just write 14 grams. Okay? That's it. Moving on. The question says, what volume of nitrogen gas at STP? Remember, guys, this just means standard temperature and pressure. In IB, they'll start to change your temperature and pressure and gas starts acting differently. You may have been exposed to this in physics, but you'll see this in IB. But here in this test, you can always assume standard temperature and pressure, okay? So what volume of nitrogen gas at STP would react with 37.2 grams of magnesium to produce magnesium nitride? So they've done this for us again. We have magnesium and nitrogen gas and magnesium nitride. So let's look and see if we can make sure it's balanced. So we have 3 magnesiums. This is like one of the easiest things. 2 nitrogens, so we're good. That was easy. We can write ones, assume ones, whatever. Here's our known. Here's our unknown, okay? So our known, 37.2 grams of magnesium. Our unknown, what the question's asking, is what volume. So remember, volume, guys, is always in liters in 10th grade, okay? Nitrogen gas, that's N2, not Ng. Now, we're given grams, and we need to answer in liters, okay? So look at our little flow chart. We're given grams. It's actually perfect on the flow chart. We're given grams. We need to convert to moles, and then we need to convert back to liters, okay? So it all depends on the question, what your problem will look like, and I think that's what freaks out many of you, because you don't know really, it's not like a formula you use over and over, it's just something you have to kind of create your own formula. And that's dimensional analysis, the crossing out of things, the converting of things, the ratios, that's called dimensional analysis, and that doesn't go away in college or IB for sure. All right, so let's go ahead and get started. So we always start with our known. Scooch this over. 37.2 grams of magnesium, and then we need to cancel that out and convert to moles. Okay, so to do that, you cancel the grams of magnesium. It needs to go on the bottom, and then you're going to you're going to put moles of magnesium at the top. Okay, 1 mole of magnesium. I like dealing with just elements because you just look at how much the element is and you don't have to add everything. That's where I make my stupid mistakes. 24. We'll just say 24. We're just rounding today. Okay. 1 second. Okay. So we have 24. Now we've crossed out our grams of magnesium. We need to do our mole to mole ratio. So moles of magnesium go at the bottom. The moles of our unknown go at the top. So N2. Okay. So now we do our ratio. Magnesium is a 3 coefficient. Nitrogen gas is a 1 coefficient. And then we move on. So whatever's up here goes here. Remember, we're just converting from moles to liters now. Okay, so 1 mole equals, and we're converting to liters of nitrogen gas. Now remember, anytime you're converting from moles to liters, you're just using this constant. It's just like Avogadro's number. You're just using the constant. So that's always the case right here when we're dealing with gas. It's always that constant, okay? Now, moving on, we are at our end. The question's asking for liters of nitrogen gas. We're here at liters of N2. So whatever we calculate is our answer. So we just take our handy dandy calculator and we do 37.2 divided by 24 divided by 3 times 22.4 equals about 11.6, we'll say. 11.6. That's it. So easy. Okay? Moving on. How many molecules of sulfur trioxide would react with 68.9 liters of water at standard temperature and pressure to produce sulfuric acid? So it doesn't have the lines, but when it does this, I like to make sure that it's balanced just for fun. For fun, yes. So sulfur, I have one sulfur. Oxygen, I have four oxygens. Hydrogen, I have two, so we're okay. So everything we can assume is a 1 coefficient. Now, we have our knowns, and we have an unknown, okay? We only have one known, so we're not doing a limiting reactant or excess reactant type issue. So our known is whatever number they give us, 68.9 liters of water, okay? Our unknown is how many molecules of sulfur trioxide, okay? All right, so we're going from liters to molecules. So again, we have to figure out, we have to actually create our own problem. That's what's, again, I think is what's so scary for you. So I already forgot what I was looking for. We're going from liters to molecules. So from liters, okay, we have to convert liters to moles and then moles back to molecules, okay? So that's all we're doing. So we always start with what we have, 68.9 liters of H2O, okay? And then to do that, okay, we have liters of H2O here. We're going to say 22.4 for every 1 mole. Okay, that's us converting to moles. Now we do our mole to mole ratio. Whatever's up here goes here. The unknown goes at the top. We did our mole to mole ratio. They're 1 to 1, coefficient 1, coefficient 1. Then we have to convert from liters, or I'm sorry, from moles, and we have to figure out the number of molecules. So the mole will go at the bottom, because we have to. Whatever's up here must go here. SO3, 1 mole. And this is where we will use Avogadro's number, 6.02 times 10 to the 23rd molecules of SO3. Okay, so we have that, and our liters cancel. The moles of H2O cancel, moles of sulfur trioxide cancel, and we're left with molecules of sulfur trioxide, which is what we are trying to find out. So we're done. Okay, so what I would do is, if you have like a ghetto calculator like me, I would do exactly what I've been doing and then times it by 10 to the 23rd. So what I would do is 68.9 divided by 22.4. It's 1 to 1, so we don't really care. If we did times 1 divided by 1, it'd be the same. And then we're going to do times 6.02. Okay, so we have 18.5. So we have 18.5 times 10 to the 23rd. Easy. Not so bad now, huh? Yeah, right, miss. Okay. So the next question says, what is the maximum number of grams of silver phosphate that can be produced from the reaction of 287 grams of silver chlorate with 52.8 grams of sodium phosphate? So we're going to do our 2 knowns and our 1 unknown. We have 2 knowns. The 1 unknown is here. How many grams of silver phosphate? So we use the same unknown and the 2 different knowns. So is it recording? Okay, my battery's dying. So we have a known, unknown. We're going to have another known, unknown. So the first known, 287 grams of silver chlorate. So that's this thing. So AgClO3. Then our unknown, maximum number of grams of silver phosphate. So how many grams of silver, that's this thing, Ag3PO4. Next known, 52.8 grams of sodium phosphate, so that's this thing, Na3PO4. And the unknown is the same. How many grams of silver phosphate? So what we're doing is we're basically seeing how much of this stuff can we make if we have this much of this stuff, how much of this stuff can we make if we have this much of this stuff. And then we're going to compare at the end, and whoever will make the least will be our limiting reactant. The limiting reactant makes the maximum number of grams. So you always start with what you know first. So the known is 287 grams of AgClO3. And then whatever's up here, we cancel, bring it down here. Again, simple dimensional analysis. Grams of silver chlorate. And we need to convert to moles. So our first step, if we don't have moles, which we don't, we need to convert to moles. So that's what we're doing. We're converting to moles. And to convert to moles is just a constant. 1 mole of silver chlorate will always weigh a certain amount. We have to find this amount, again, on the periodic table. So we have silver, okay? Silver weighs, where is silver? Here. Sorry, that's gold. Silver weighs 107.8. So we're just going to say 108. So silver weighs 108. So we're going to type in 108 plus, and there's chlorine. Chlorine, looking at the periodic table, weighs 35 grams per mole. Oxygen weighs 16, so we're going to add plus 16 plus 16 plus 16 because we have 3. Okay, so 191. All right, so we have our first step. So now this basically converted to moles. Now we need to do our mole to mole ratio so we can start talking about our unknown. So whatever we're trying to get is going to be our unknown. So we need to convert to moles of unknown, which is Ag3PO4 over the moles of whatever we need to cancel out. So the moles of the known, AgClO3. And then to find out what numbers go here, we look at the coefficients. So moles of Ag3PO4 here, we can assume 1. Moles of silver chlorate, here we write 3. Moving on, we need to get out of moles because this would give us answers in moles because these two would cancel, these two would cancel, and we'd have moles of silver phosphate, but we're actually not wanting moles. We have to do this step, so we have to convert to that, but we want the answer in grams, so now we gotta convert out of that. So to do that, we need to put this at the bottom always. In dimensional analysis, the unit here that we're trying to cancel out goes at the bottom. Moles of silver phosphate, we cancel, and we need grams of silver phosphate. And it's always 1 mole because it's just a conversion. Now we need to find out how much this thing weighs. So to do that, you just look up on the periodic table. So there's 3 silvers, and remember silver weighed 108, so we're going to add 108 3 times. And my calculator is dead. Oh, sorry, I forgot there was it's solar powered and I was blocking the light. So we have 324 just with the 3 silvers, sorry. Now phosphorus weighs 31 grams per mole. Plus 4 oxygen, so we're going to add 16 4 times. I actually don't remember how many times I added it. 2, 3, 4. 419. Okay, I did it one too many times. 419. All right, that's going to be our answer. So now we just do the calculation. So we have 287 divided by 191. We ignore the 1, so we just do divided by 3, and we multiply it by 419. And you have 209.8. You can round it to 210 if you want to. 210. 210 grams of sodium, not sodium, 210 grams of silver phosphate, okay, is the first answer. That's not our answer, but that's the first thing we're going to compare. Now we have to do this thing. So we're going to start with the known, 52.8 grams of sodium phosphate. Whatever's up here, the unit, it goes down here, grams of sodium phosphate. And we just have to find out how much that thing weighs. And then up here will be 1 mole because we don't have moles and we need to convert to moles. Okay, and then of course this will be a mole to mole ratio. We already know that, but right now we need to find out how much this thing weighs. So sodium, if you'll look on the periodic table, it weighs 23 grams, and we have 3 of them. So 23, 23, 23. Then we have a phosphorus, which weighed 31, I remember, and then 4 oxygens. 1, 2, I'm going to count out loud because I'll forget. Okay, so 164 grams. All right, and then we do our mole to mole ratio. What's up here goes here. Na3, PO4. Up here's the unknown, Ag3, PO4. Ag3, PO4 is 1. Na3, PO4, 1. We don't want moles, so we need to cancel that out and get grams because the question's asking for grams. Moles of, Ag3PO4 over, we already calculated, I'm not going to do that again because I am very slow at that, Ag3PO4. Then we just plug it in the calculator. Handy dandy calculator. Okay. 52.8 divided by 164. We're going to ignore the ones. Times 419. 134 point, we'll just say 134.9. So 134.9. And that's grams of that silver phosphate. Okay, so essentially what we did was we said, if we had this much of this stuff, how much of this can we make? And if we had this much of this stuff, how much of this can we make? And if we had both of these, with us, what's the maximum number of this can we make? We can't make any more than our limiting factor, right? We can't be any stronger than our weakest link in a chain. We can't make any more sandwiches than the lowest ingredient that we have. If we have 100 pieces of bread, again, like I've said, and we have 3 pieces of cheese, we can still only make 3 sandwiches. We can't make 50, okay, because we don't have enough cheese. So that's what we're looking for, the lowest number. So this is the lowest number, so this is the maximum number of grams. So make sure you read your question too. The question is, what is the maximum number of grams of silver phosphate? It's not asking for limiting reactant, it's not asking for excess, it's asking for the maximum number of grams of silver phosphate that can be produced. That's this. This is the maximum number. If it asks for limiting reactant, we would say sodium phosphate, okay? But it's not. It's asking for the maximum number able to be produced of this. So that's the answer. Okay, moving on. Okay. Now, how many formula units? So we're asking for formula units. I know I'm going to need Avogadro's number. Of iron oxide of iron oxide can be produced from the reaction of this many grams of iron with this many liters of oxygen. So we have two knowns, we have one unknown, it's going to be that two-step problem, and then we have to compare. What are we comparing? We're going to ask how many literally it's asking how many molecules can we make given grams of this and liters of this. So there's going to be some conversions going everywhere. All right, so our first known and unknown, known, unknown. This is how I set up my problems. The known, 108 grams of iron. The unknown, how many formula units of Fe2O3? Okay. The second known, 72.1 liters of oxygen. The unknown is always the same. Always, always, always the same. Okay, so I know a lot of you are probably saying, oh my gosh, Ms. Passons, you haven't balanced it. That's okay. Oops, sorry, y'all didn't see that. That's okay if you haven't balanced it. You need to balance it for sure before you get to the mole-to-mole ratio, okay? Because that's when you have to figure out those coefficients. So we have 2 irons, we need 2 irons. 2 oxygens, we have 3 oxygens. So that's that annoying thing where we have to kind of, we'll put this here, we'll put this here. So our oxygens are balanced. This is only 1, so it's going to be easy. So now we have 4 of these, so we're going to mark that out and make 4. Okay? All right, so moving on, we're going to put we need to convert grams to moles, always to moles, if it's not already moles. So grams to moles, and then we need to convert to formula units because that's where we want to end up. We start with grams, we need to end up with formula units. Okay, so we're going to start out with 108 grams of iron. And we need 1 mole of iron. And over grams of iron. So iron weighs about 56 grams per mole. So 56 grams of iron for every mole. And then we do a mole-to-mole ratio, of course. We can't do stoichiometry without mole-to-mole ratio. Known goes at the bottom, unknown goes at the top. Coefficients, we get our numbers from our coefficients, 2, 4, and then we convert to formula units. So FUs go on top, FUs of Fe2O3. On the bottom, the mole. We have to cancel out that mole, Fe2O3. Now, formula units of that, so we don't have to find the mass because we're looking for the number of molecules. So that's the whole Avogadro's number, 6.02 times 10, wow, 10 to the 23rd. That's the 23rd, sorry guys. But you know that number, you should. Okay, and then whatever that equals is what it equals. So if you have a ghetto calculator like me or Cheeto, you will have to just kind of improvise. So what we're going to do is take 108 divided by 56 times 2 divided by 4, and yes, you could just say times 0.5, times, I'm going to put 6.02, and then whatever my answer is, I'm going to equal it to 10 times 10 to the 23rd because my calculator is the one I stole from Mr. Kramer. So the answer is 5.8, so I'll put, the answer will be 5.8 times 10 to the 23rd formula units of Fe2O3. That's my first answer. Can y'all see? Okay. All right. Let's do the second one, and we're going to compare because we just need to compare the maximum amount of formula units, how many formula units can be produced. So let's set up this problem. We always start with our known, which is 72.1 liters of oxygen. We need to get rid of the liters, so liters of oxygen go on the bottom, moles of oxygen go on the top because we got to convert that into moles. Liters, this is a constant, that's that 22.4. Okay. Now, of course, we do a mole-to-mole ratio, moles of O2, because that's the known is on the bottom, the unknown will be on the top, the Fe2O3 right here. Okay, we get our numbers by looking at coefficients, 2, 3. Okay, now The question's not asking for moles, it's asking for formula units, okay? So we need to formula units of Fe2O3 over 1 mole of Fe2O3. Okay, and this is Avogadro's number, 6.02 times 10 to the 23rd. Let's make it a little bigger here so that you guys aren't like, what is she doing? Okay, now again, I have this calculator. We're going to calculate things. So we have 72.1 divided by 22.4 times 2 divided by 3 times 6.02. So we have 12.9, and we're going to add the times 10 to the 23rd. So 12.9 times 10 to the 23rd formula units of Fe2O3. Just like that. So it says how many formula units of iron can be produced. So we're looking for the lowest amount. So this is the maximum number, okay? This is the maximum number we can produce because it's the lowest number, okay? Just like the maximum number of sandwiches we can make with 100 bread, 2 cheeses is 2 sandwiches, okay? So this is excess, this is a limiting, this is limiting, so this is the maximum we can produce. Okay, moving on. How many moles? So, so we're going to moles of barium hydroxide can be produced from the reaction of 4.234 moles. Oh, cool. This is just moles to moles. That's great. That'll be quick. So we're going to moles to moles, so we don't have to deal with converting from grams or liters, grams, or formula units, or whatever. So we have 2 knowns and 1 unknown. Okay, so our first known is 4.234 moles of barium, okay, and then the other known is 8.902 moles of water. The unknown is how many moles of barium hydroxide can be produced. So how many moles of barium hydroxide can be produced? So how many moles of barium hydroxide can be produced? Okay, so we're going to do our 2 equations. They're going to be quick because we don't have to convert from grams to moles or anything. We already have moles. So we start out with what we know, even though it's still moles. We still start out with what we know, moles of barium. We cancel out moles of barium. We need our moles of unknown, which is barium hydroxide. Okay, we do our coefficients, 1 and 1. Wow, that's just super easy. So the answer is literally what the same, 4.234 moles of barium hydroxide. Now, if you were like super smart, you would say, oh, it's a 1-to-1 ratio. If it's this many moles of this, it's this many moles of that. Okay, that's fine if you're like that great. I'm not, so I don't do that. Now we have moles of H2O. So we have 8.902 moles of H2O. We need to cancel out that known so we can get our unknown. So moles of H2O will go on the bottom. Our unknown, moles of barium hydroxide, will go on top. And we look at the coefficients. We have barium hydroxide is 1, H2O is 2. So basically, if you want, you just divide by 2. So 8.902 divided by 2. And the answer is 4.451. 4.451 moles of barium hydroxide can be produced by this. It needs a parentheses. Okay, so it's asking how many moles of barium hydroxide can be produced. So the maximum amount is the lowest amount. This is the maximum we can produce is 4.234. So that is the max. Okay, last video, well, this is my last video. I've done this 3 times, but last problem is has to do with excess reactants. We're not really going to have a lot of excess reactant issues, problems on the test. It's just you're just going to identify the reactant that's in excess. You're not going to calculate it. We didn't have time for that. What is the maximum number of grams? So we have, I see we have a known and a known. So we're going to have two knowns and two unknowns. Okay, so our first known is 67.8 grams of nickel. And our second known is 37.3 grams of bromine, Br2. Okay, and our unknown, it says what is the maximum number of grams of nickel bromide. So how much nickel bromide can we make if we have these two amounts? Okay, what's the maximum? So we always start with our known, obviously. So we have grams. It's asking for grams. We have to go from grams to moles and back to grams. So we have 67.8 grams of nickel. And we need to convert to 1 mole, or we need to convert to moles of nickel. So we need to find out how much nickel weighs. On the periodic table, it says nickel weighs 59-ish. 59 grams per mole of nickel. And I do not have any eraser, so we're going to put our little dot like this. And we know there's a mole-to-mole ratio, always, right? Nickel will be on the bottom, the known is on the bottom, the unknown is on the top, NiBr2. Okay, and we look at our coefficients, which we didn't do, which probably you guys are like, Miss Passons, we didn't do it. Okay, fine, we'll do it now. 1 nickel, 1 nickel, 2 bromines, 2 bromines. Okay, it's a 1 and 1 and 1, right? Am I going too fast? No? Okay. So it's a 1-to-1 ratio. So now we need to get it out of moles and bring it back to grams. So grams of nickel bromide over 1 mole of nickel bromide. That's how we cancel out this mole. Okay, and now we have to calculate. Oh, I have to calculate how much that weighs. So nickel weighs 59, like we said. Okay, and we need to add how much bromine weighs, which is, I can't see because of my computer and the phone. Sorry, guys. 80. We'll say 80. Okay. So it weighs 80, and there's 2 of them, right? Plus 80 plus 80. So it weighs 219 grams per mole. 219 grams per mole. So now we just calculate it. 67.8 divided by 59 times 219, and that's 251.7, I guess. 251.7 grams of nickel bromide. Okay, now we do the second part. So we have 37.3 grams of bromine, sorry. So we need to cancel out the grams of bromine. Bromine weighs 80, so I'm going to 80 plus 80. So it weighs 160, so 160 grams of bromine over 1 mole of bromine. This is how we convert to moles. Then, mole-to-mole ratio. Known goes on the bottom to cancel it out. So we can start talking about our unknown, which is on the top. I put a B here, but it's bromide. It goes here. And we need to look at it, it's all 1-to-1 ratio, so 1-to-1. Now we need to convert this to grams of nickel bromide, sorry. We have like a few minutes until 8th period starts. I'm sure I'm gonna have Nick running in here and gotta get this done. 1 mole of nickel bromide over however much it weighs. And we went ahead and calculated up here, so I'm gonna just trust myself, which is probably a bad idea, but time restraints force us. Now we do our calculations. 37.3 divided by 160, ignore that, times 219 equals 51 grams of nickel bromide. I keep trying to do boron and nitrogen. Okay, so the question actually asks, what's the maximum number of grams of nickel bromide that can be produced? We're going to look for the smallest amount. So this is the max. That's the max because that's the least. Just like that whole cheese bread thing, I'm not going to beat you with that analogy, but it's the maximum. Which reactant is in excess? So which reactant is in excess? This, so excess, don't get trolled and say, oh, this is excess. This is not excess. This is theoretically how much this can produce. So the actual reactant in excess is whatever would make the most theoretically, okay? So this is limiting, this is excess, okay? Excess just means too much. If you have 2 pieces of cheese, 100 pieces of bread, the bread would be excess. Think of it that way, okay? So this is excess, this is limiting. The cheese is limiting, the bread is excess, okay? I know that's so simple, but I mean, with these crazy molecules and words, and you may want something simple. So this would be the excess, is nickel. Okay? So reactant in excess is nickel. The maximum amount made, this. Okay? Good luck, guys.